Okay, we go.
Questions on the homework? A lot of it was just fact checking the axioms, I think. This is 4.1. Questions?
Yeah, the 13. It's like verify the axiom of 3, 7, 8, and 9 from vector space in term 4.
We want to verify axioms.
3, 7, 8, and
What was the example?
example 4 from the textbook.
U is equal to U1 1. This is a matrix.
Oh,
It's a 2 by 2 matrix.
okay.
U is equal to U1 1, U1 2, U2 1, U2 3. V is equal to V1 1. Same thing.
Okay.
V is equal.
Okay.
And W.
And there's a W matrix vector.
Yeah.
Okay. And how did we define the operations?
Oh,
What did add mean? Addition meant what?
U plus V equals U1 plus V1, U2 plus V2. That's what it was. Like for the usual.
The usual addition? Okay.
Yeah, usual.
Okay. And what was the scalar multiplication rule? Huh? It's also the usual thing?
Yeah.
Oh, so. Alright. What were axioms 3? Is that associativity?
Yeah.
Okay. So we just want to prove that U plus V plus W, if I add those two, I get the same as U plus V plus W. Right, so this was axiom 3. And so you can check. So I know that U plus V plus W is equal to U11, U12, U21, U22 plus V11, V12, V21, V22 plus W11, W12, W21, W22. This is U11, U12, U21, U22 plus V11 plus W11, V12 plus W12, V21 plus W21, V22 plus W22 equals V11 plus V11 plus W11, U12 plus V12 plus W12, V21 plus V21 plus W21, U22 plus V22 plus W22. Now when we're here, these guys are just real or complex numbers, so I know associativity will work in each component. So inside I can move the brackets here if I wanted to. Yeah, a lot of these things are just writing them out and you check the properties. W1, W2, which is basically equals to U plus B plus W. This step happens by associativity of real numbers. On F. Yeah, like everything would be similar. You combine the matrices, you do your voodoo inside the components, because inside the components you have real and complex numbers, and all the 10 properties work on real and complex numbers. So the others also done component-wise. So yeah, kind of annoying to write it all out, but it's essentially, they want you to just check that. I thought they'd at least give you something interesting, like some weird operation. Any other questions? 19. What did that say? Wait, V equals the vector space of? All real numbers? So V basically equals R, yeah?
This is positive real numbers, you got numbers.
Positive real numbers.
Yes, then the vector is equal to U, the n vector is U. And you write the vector statement has a statement about those numbers.
Okay, so what were the operations that you talked about in this example?
Negative U is equal to negative 1 times vector U. That was the question.
No, this is referring to something in an example she said, right?
Example 8, okay.
Example 8. In example 8, what were the defined operations?
We said U plus V is equal to UV,
U plus V is equal to UV.
and then KU is equal to
KU is equal to U to the?
K.
Okay, so the define adding two vectors, and I'm just saying U. Well, I can just call them U and V. These are elements in the positive real numbers, and then when you add them, it defines addition as multiplying them, and it defines scalar multiplication as raising to the power K. Okay, and what do we want to show?
U is equal to negative 1 times U.
So negative U is equal to minus 1 times U. Okay, so to show that the negative of a number is in this vector space the inverse of the number, basically is what it's going to ask you. How would you figure that out?
U plus negative U is 0.
First of all, right, we need to show that minus 1 times U plus U is equal to the 0 vector. What is 0 here? The 0 vector is 1 here. 0 is equal to 1 in this vector space. How do you know?
As U plus 0 is U.
Right. Since if I take U plus 1, the result is 1 times U, which we know is U because I proved that in the theorem. 1 times U is U in a vector space. And so also 1 plus U, well, let's do it this way. This is U times 1, and that U. This is 1 times U, which is U. This means that your 0 is equal to the number 1. Okay. So now I want to show Thus, we must show that if I take -1 times u plus u, the result will be the number 1. Now, by definition, how is this defined?
u to the minus
U to the -1 plus u. So that's what I need to show. Let me see. So note that -1 times u plus u is equal to u to the -1 plus u, which addition in this vector space means multiplied. And so that gives us the number 1. That proves it. Was that the only question for that problem 19? Yeah. So a lot of things really happened here, so let's actually go over it. We're working in real numbers, but it doesn't actually make it any more clear, I don't think, because we're thinking of things in a different way, right? So in this space, addition is the same as multiplication, right, in the usual sense, right? We're only looking at positive real numbers, so we're not including 0 or anything like that. And our scalar multiplication is replaced with the operation exponentiation. Now we need to show this. So first thing you have to do, you have to understand what do you actually have to show that, right? Our notation, when we say minus something, minus an element in a vector space, what does that mean? Well, one of the axioms told us what that means. The negative is just something that you add to the original to get the 0 vector, right? Now again, 0 vector does not mean 0. It does not mean 0. The 0 vector is the guy that when you add to someone, you get himself, okay? So when we're looking at these operations to figure out how things work in this vector space, I need to show that if I add this guy to u, the result is going to be 0. I first need to figure out who the hell is 0. So then I have to figure out what is 0 here. What is the guy that when I add to someone I get himself? Well, since addition is the same as multiplication here, the real number 1 would function as the 0 vector. So now I know that, okay, what I want to show is that when I add this guy to that guy, I actually get the 0 vector, which in this case is the real number 1. And because our scale multiplication is exponentiation, and our addition is now multiplication, we ultimately can get 1 by adding this, and we've thus proved the claim. Right? So this goes back to what I was saying. Don't think that things are obvious, like everything that works, how the real number works is how everything else is going to work. You want to be abstract here. You want to think in general. You want to think, define something not in terms of its name. Oh, 0 must be 0. No, you define something in terms of what it does. Something, you call it 0, when you add it to something, you get itself. Something, you call it 1, if you multiply by something, you get itself. Something you call a negative, if when you add it to that thing, according to whatever rules of addition you're using, you get the 0, right? Which could be whatever thing fulfills this property, right? So you really want to get to the point where you're thinking in terms of properties and what something does, the duties it performs, instead of, how it looks or what its name is called, right? I think with that we can jump. Most of this homework, it seems to me, was just like going through the axioms and checking, is this a vector space? And then you go through the list and see if it fulfills all of them. It's mostly a lot of writing, but it shouldn't have been too complicated. So you can pass up those homeworks. We will forge ahead. I want to actually do 4.2 and 3 today, and maybe have a little talk at the end about proofs, but we'll see if we get to that. We will see if we have the time. So most of my examples, I worked them out ahead of time, and it's not really something we need to know how to do now because we did it in chapter 1. So things should go by faster, and hopefully we can get through the chapters, the sections. So we're actually continuing with subspaces. And last time I believe we ended with an example that we didn't complete, so let me just complete that for you and we will talk about it. I don't remember, what was that question actually? Wasn't the same. Right, actually for a bunch of vectors span the set R3. Okay, so, which is exactly the same kind of example we ended with last time, so let's actually do that. Determine the set of vectors span R3. And our first set of vectors were 1, 2, 1, 0, 1, 1, minus 1, 0, 1. Our second set of vectors, 1, minus 1, minus 2, 2, 1, 1, 0, 0, 1. And our third set of vectors was just a set of two vectors, 1, 0, minus 1, 0, 3, 1. Okay. So you go with part A, right? So what do we mean by it spans the set? That was also something I asked you again on the quiz for a second time, so hopefully you guys know the definition by now. What does it mean to say a set of vectors spans a space? When I say these vectors span the space, what am I saying? What do I mean?
A linear combination of them can get you any vector in the space.
Right. We need to see if for any, and I do mean any, v in my vector space R3, that C1 times 1, 2, 1 plus C2 times 0, 1, 1 plus C3 times negative 1, 0, 1 can give me that vector v. That's the goal, right? Once that, if this is consistent for C1, C2, and C3, then I can say yes, it spans the set. Now this I can write as a matrix equation, right? Where my C1s, my C's are like the variables. So when I throw these all in a matrix, it just amounts to lining up these vectors. And let's say I call my v the vector x, y, z, right? I just pick a random guy represented by x, y, z. I want to see, is this system consistent? Can I actually find a solution for C1, C2, and C3? And if I can, that means it spans the set. Right? So it turns out the reduced row echelon form here was actually, I worked it out, 1, 0, minus 1, 0, 0, 1, 2, 0, 0, 0, 0, 1. That was my reduced row echelon form, right? So first here, one way you could have checked, you could have quickly checked what was the determinant. Here you got the determinant was 0, which means you either have no solution or infinitely many. So to make sure I rule out the infinitely many case, maybe I could express these guys as x, y, z. I did a row reduction instead, but what did I end up with? There's a 1 here. I have 0 plus 0 plus 0 equals 1, inconsistent. This means there's no solution for C1, C2, C3. This means they do not span the set. So this is what span means. If you take a random guy in your vector space, then a linear combination of those vectors should be able to give you that vector. If that's true, we say it spans the space, right? So I picked a random guy here, set up this equation, I can transform it to a matrix, and then by knowing stuff about matrices, which we did in chapter 1, I can determine things like this. If I realize that this guy here, I call this coefficient matrix A, if the determinant of A was non-zero, I know that a solution exists, right? I know by Cramer's rule for one example. And I know, for example, that the reduced row echelon form of this would be the identity from that big theorem, and we will definitely be able to have a solution here. So that was one way. If you get a determinant is 0, though, you might have to do some extra work just to make sure that you don't have like an infinite number of solutions. Let's go to B. So in B, basically, we do something very similar. We'd set this up, 1, minus 1, minus 2, 2, 1, 1, 0, 0, 1, with x, y, z, some random vector in R3. Notice here, if you did the reduced row echelon form of this guy, you'd actually get the identity here. In fact, if I call this guy A, the determinant of A was, I believe, 3. And the reduced row echelon form actually looked like, did I do it? Yeah. You have this, and then you have A minus 2B all over 3. Then you have A plus B all over 3. Then you'd have A minus 5B plus 3C all over 3. So you could have found the determinant, and once it's 3, you know there's a unique solution. Or if you wanted to follow it out, you can, which you might have to do in some cases if you want to, you're after coordinates or something like that, which we'll get to in 4.4. If you want to actually work it out, you can realize here, there's a consistent system here. All I have to do is set C1, C3 equals this, C2 equals that, C1 equals that, and this equation will actually be solvable for this set of vectors. So this means it does span R3. Because any random vector in R3, I can let it, I think I put ABC for the second one. So coded turns in. So this actually does span R3. And our third example C. Now we haven't really dealt a lot with this yet because we haven't really spoken about dimensions, but if you had given me an answer like this, I would have accepted it. You can say it does not span. Since, why?
There's only two elements in R3.
There are only 2. And the dimension of R3 is 3, which means you need at least 3 vectors to span a vector space of dimension 3. You need at least n vectors to span a vector space of dimension n. I know we didn't deal with this yet, but if you had written this down, I would have given you the points, because it means you're reading ahead. But we could have as well went straight into this sort of treatment and actually set up the system, right? Or we could check the consistency of this system. So I throw these guys into a matrix. 1, 0, minus 1, 0, 3, 1, and set this equal to x, y, z. And did I actually write that down? Please tell me I did. And it did. So if you found the reduced row echelon form of this guy, it would have been 1, 0, b minus 3c over 3, 0, 1, b over 3, and then 0, 0, 0. So what does that mean? So let's say you weren't sure how to deal with this, and you start to set up the system, and you got to this point. What could you conclude? Tell me why.
because it's consistent, and then the last one gives you that zero, parametric. In other words,
Yeah, but why is it why is this a problem?
what if there's a free though?
Is it because there's only two solutions? Is that a problem?
Well, tell me, what would this mean? How would you interpret this result here? Now remember, ultimately what we were trying to do, we were trying to say C1 times this plus C2 times that equals this, right?
There's infinitely many solutions, but it has to equal one, it has to be a linear combination that equals one particular vector, but because it can be any vector.
Because it can be what?
Because it can be any vector,
And then
because it has an infinitely many solutions.
This is y 3z y over 3.
So does that tell us that C2 is equal to y over 3?
Yeah.
And then C
So we know that C2 is equal to y over 3.
and C1 is equal to y minus 3z.
C1 is y minus 3z over 3. C3 can be anything. What does that actually mean?
It's not a linear combination.
Why not?
It doesn't.
Because it can be a scalar or a vector?
No? My x, y, z here are constants.
Okay. So it's-
That's why sometimes you say a, b, c, so you don't confuse them. They're actually constants. So this is just a number, that's a number. This can literally be anything. So I can pick any scalar for that I choose, right? So if I take y over 3 times vector 1, 0, minus 1 plus y minus 3z over 3 times 0, 3, 1 plus anything. Well, there's no guide here. Are we sort of seeing what the problem would be?
We're going to
that-
multiply by it?
I forgot we're only doing 2. We only have up to C2, right? Okay, so I got C1 is this, C2 is this, but according to this, what would we have here?
C1 and C2
It's a multiple of.
I could have, row 3 would tell me that C1 can be anything, or C2 can be anything, right?
Mm-hmm.
But is that the case? Well, no, I just said no, they have to be these specific guys. And then I come back and I say, they can actually be anything. It's not actually consistent, right? You'll have a contradiction here, right? So I could say, if C2 equals y over 3, then we cannot have C2 equals t, where t is arbitrary.
It's like it's giving us two different.
It's giving us 2 different answers. It's like I'm telling you, the answer has to be 3. It definitely has to be 3. And then I'm like, actually it could be whatever, right? That's not consistent, right? Which is it? Does it have to be this, or can it be anything? Right? So. You run into trouble. You can't actually determine at least one of those variables. You can't actually solve that equation, that system. But the nicer argument is definitely dimensions, but technically we have to wait till 4.4 to properly make that argument.
Don't we take the intersection of the solutions? The third line is telling us C1 and C2 could be anything, but the first two saying they have, like, let's say C2 has to be y over 3. So the intersection of the solution is y over 3. I don't see any contradiction there.
Where did you get this intersection of solutions idea?
Because let's say, like, if it's a equation, if it's like equations, you can to any set of equations you can add zeros, zero line to the bottom of any matrices. It is not a contradiction to the previous equations, I believe.
Well, did you actually try to set this up? I mean, if you actually wrote out the equations.
I mean, for any equation,
Let's say my C1 is, let's say I take the intersection like you said, and I said this guy, 3z over 3 times what were our vectors? 1, 0, minus 1, plus y over 3 times 0, 3, 1. See, that idea of the intersection of solutions doesn't really work. And this was supposed to give me x, y, z. Do you see a problem here?
no, I don't see a problem.
How would I get an x?
1 times that.
Okay,
1
so I have
times
y minus,
3 is 0.
I have y over 3 minus z
is
must be x.
yeah.
Okay, so this would mean that my x plus, my x minus y over 3 plus z must be 0. But what does that tell you? Can I pick any coordinate I feel like?
We're not picking any coordinate.
We are picking any coordinate. That's the point
No,
of span.
But that's like those are C1s. C1 is only
Right, this is my C1, this is my C2. And I want
You
to
cannot-
show that I
yeah.
can make a linear combination of these
you
two
cannot
vectors.
write that for I got it for all the vectors in
Right.
in R.
So I want to show, let me just spell it out so to make sure if anyone else is confused. I want to show that a linear combination of these two guys can give me anybody.
Yeah.
Literally anybody. But this cannot give me anybody. This can only give me the people where this is the relationship between their coordinates.
Yeah.
Right? Once I get something that's superfluous, I have to, it forces a condition on the guys where I can't pick anyone I want. Right? So anyone who the coordinates don't have this relationship, I can actually never get them. Right? So I can get a few people, I can get maybe a subspace of R3 with this, right? I can form a plane with these two guys, and then I can say it actually spans that vector space, the plane, but it doesn't span all of R3. The fact that I can only solve for 2 constants when I need 3 of them to get to this guy, this guy, this guy, which again we'll understand more when we get to 4.4, that actually messes things up a lot. Right?
Professor?
Yes.
So, since you're speaking like how it looks, like the graph looks, so you're saying that these are two vectors that intersect and they span a plane that contain one.
I could create a plane that contains these two guys.
Okay.
I could.
Okay.
Yeah. I could create a plane that contains these two guys, just like in Calc 3. You know, you just do like the cross product, get the normal vector, pass through one of the points. But yeah, that's still not all of R3. Right? There's going to be, it only restricts this guy. In fact, this is a plane that I could create with these two. Right? So only points that land on this plane can be spanned by these vectors, not all of R3. And in fact, this is actually a far more general thing, which when we get to 4.4, we'll understand more. If you have an n-dimensional vector space, you need at least n vectors to span it. Yeah, so I think that actually did that example last time. Let's talk about another idea. A couple more definitions before we end here. Let A, B, and matrix. we're going to define this guy we call the kernel. We think of these as the solutions to the homogeneous system. That solution set we call the kernel. This is called the kernel of A, this vector space. And we actually proved that this was a vector space, I think, last class. No. I want to get a little bit more specific here. The kernel is actually a vector space of phi. So it's the set of all inputs that you can plug into the system that gives you a zero output. We call that the kernel, and it's a subspace of the input space. One other important idea I want you to note here. Note that spanning sets of a vector space are not unique. We'll revisit this idea when we get to bases. Example. I think I've shown you a couple times now. We know that I, which is equal to 1, 0, and j, which is equal to 0, 1, span R2. But these two vectors, 1, 1, and -1, 2, also span R2. So there's not a unique way to span any given set. That's what I basically want to talk about, say here. Note, if AB is in R2, then the system, I can set up the system with these vectors, 1, 1, -1, 2, AB. That would reduce to ultimately 1, 0, 0, 1. 2a plus b over 3, and b minus a over 3. And so you can literally say this times this vector plus this times that vector will give you the vector ab, and you can actually do the computations and check it. One more theorem here, but I don't think we care about all three. I can't think of an example I'm going to give you guys where you actually need to know it up. So that is 4.2. 4.3, linear independence. We've been talking about this for a while, but let's actually do it yet again. Definition. So linear independence, we say a set of vectors linearly independent set if none of the vectors in that set can be expressible as a linear combination of any others, right? So there's no linear equation that will relate them that you can have for n minus one of them that describes the last one. So you say it's independent of description by a linear equation. You call it linearly independent. A very important idea. The definition I gave you before actually comes from a theorem that I'm going to mention now. Because that definition is actually too vague to work with. So we have a theorem that says that S be a set of vectors then we know that S is a linearly independent set. If and only if the only solution to C1 V1 plus C2 V2 plus Cn Vn equals 0. 0 is the 0 in the vector space. For the constant C1 all the way to Cn is C1 equals C2 equals Cn equals 0. If the only solution for the constants is the trivial solution, we call the set. We know that the set is linearly independent. If and only if, do we know what that means? The implication goes in both ways. This means if we know the set is linearly independent, then this will only have 0 solutions, the trivial solution for the coefficients, and vice versa. If we know that this has only trivial solutions for the coefficients, then the set will be linearly independent. I'll probably prove this next time. Don't have time to prove it. I have like 5 minutes. Might prove this next time. It's not a super hard proof. We'll see if I prove it. Examples: E1, E2. These are the guys I defined last time. Are linearly independent. In Rn. Right, these are just the guys that have 1 in the first coordinate and 0 everywhere else, or 1 in the second coordinate and 0 everywhere else, and so on and so forth all the way down the line. These are linearly independent. I actually talked about that example last time. Just wanted to remind you of that. Another one example I was going to work through is the set 1, 2, 1, 0, 1, 1, minus 1, 0, 1. Form a linearly dependent set on R3. To show that, I just have to show that there's a non-trivial solution to that. Since set C1 times 1, 2, 1 plus C2 times 0, 1, 1 plus C3 times minus 1, 0, 1 equals the 0 vector in R3. This would give us the system 1, 2, 1, 0, 1, 1, minus 1, 0, 1, 0, 0, 0. This is actually consistent. Well, let me show you what it. This actually reduces to. This side will always be 0, 0, 0. We know a homogeneous solution always has at least one solution. That was also on a quiz. I think I actually told you that in class as well. But this reduces to 1, 0, minus 1, 0, 1, 2, 0, 0, 0. So in fact, since I know at least one solution exists, there's no way it's inconsistent. It's definitely consistent. There are infinitely many solutions, which means solutions other than the trivial solution exist.
All zeros. Like everything just equals zeros.
Yeah, there's always a solution. The trivial solution will always be a solution, right? If I plug in 0, 0, 0, I'll get 0, 0, 0, right? But that's not always the only solution, right? When you're talking about linear independence, you're talking about it's the only solution. Example. This set is linearly independent. 1 minus 1 minus 2. 2, 1, 1. 0, 0, 1 is linearly independent. Right? Again, we could have mentioned here that the determinant of the coefficient matrix is actually 0, so we know that there's no unique solution. But since we know there's at least one solution, namely the trivial one, we know there's infinitely many. But this guy would be this. Which reduces to the identity. So the trivial solution is the only solution. C1 equals C2 equals C3 equals 0 is the only solution. Which means linearly independent. Also, determinant of the coefficient matrix was non-zero, which again implies that. Just because of how we know homogeneous systems behave. We will stop there. So 4.2 is due on Wednesday. And yeah, we'll finish up 4.2 as well and get the basics. And maybe I'll talk about proving stuff next time. Some of the things I was seeing on the test when I asked you guys to prove stuff, I thought I should probably mention some things. Okay, see you Wednesday.